Okay, sir.
As we continued our discussion on deconvolution, so what is the deconvolution? We have discussed in the last class, deconvolution is a mathematical tool that extracts the drawdown type curve from the rate and pressure history which we record during the well testing. So deconvolution enables us to reconstruct or compute an equivalent constant rate drawdown response for all production and certain periods combined. Okay, so we'll discuss today how actually the specific data will help us to reconstruct the well information right from the wellbore to air from the wellbore. Okay. So that means with the help of the recorded parameters, we try to reconstruct the reservoir or the reservoir parameters with the help of deconvolution. So what are the deconvolution steps we follow? So generate a type curve as an initial guess. So what we may have to start with an initial guess of our specific values. Superpose this type curve with historical rate data to calculate synthetic pressure. So what we'll try to calculate the pressure for all tests performed in the specific well. Calculate the error between the calculated pressure and the measured pressure. So we now check so that we could match both our synthetic pressure which we calculate and the measured pressure. So if it is not matching, then again we repeat the process with slightly modifying the information and then again try to match it until it is not matched. Okay, so this is how we go ahead for doing our deconvolution process. Okay, so deconvolution type curve can then be analyzed using conventional diagnostic analysis technique to determine various reservoir characteristics such as the permeability, skin, reservoir size, well location, everything. Okay. So deconvolution provides an alternative to convolution diagnostic analysis and can show additional flow regime information that would not normally be seen in the specified time frame of the build-up test. What that means, whatever specific time we conduct, your compressible zone will reach up to a certain level. But if we perform a deconvolution analysis, it helps us to predict or it helps us beyond the specified time frame we test. Okay, so this is one the advantage of the deconvolution. That means it will give us some extrapolated information beyond the test of the time also. The guidelines are very important. I'll today discuss the same thing. So what that data should be very specific. Okay, so this specific topic I'll discuss and elaborate today. So I'm just doing it. So what is happening actually? So during the deconvolution study, what we do is actually we gather information of our specific flow rate and pressure. So now we are giving input, which is actually the flow rate, and system will give you output, which is the pressure. So now what are the system characteristics that we try to understand with the help of response function. Okay, so the response functions actually the system reservoir parameter. So that we wanted to get the information. Okay, so what is the practicality related to deconvolution? So in most applications, performing deconvolution for formation and well testing pressure transient data set is not a fully automated operation. That means it is not automated. We may use certain software or maybe some program, but the important part is the input parameter is very much specific, and input parameter will guide us how accurately our interpretation should be. Okay, so today we'll discuss with specific two examples, that is synthetic example, and then rest of the part is your responsibility as an assignment form. Okay, so that you will do in your own lecture preparation. I'll select that. Okay, so that means you see the data considering pressure data for the entire test duration. Okay, so how we are going to do considering pressure data recorded only during build up. That means segment wise information we could input and get the whole information of the reservoir. That is one of the advantage of specific deconvolution. Considering only consistent build up. So you see you may have sequence build up. First build up, then you have to do something flow after flow test, then you are going for a second build up. That means you may have some noise in first build up, so you can take the second build up. So that is how, that is very much important for selecting the data which are basically not very much noisy. Simplifying the rate history before the pressure data subset to be used, okay, and excluding some production period which are actually not giving us much more positive information. So that means what is a very important part is here, the very advantageous is there. We could select a specific test which we think is a very much good test, and the data is very much authentic to go for a deconvolution analysis. So this is how the advantage related to our part. So deconvolution parameter selection, applying some default error bound, refining default parameters, okay, using constant error bound values and weighting factors for or making those specific to the subset. So that means what you are trying to get some default value for a specific test you have conducted. Okay, so use the constants or fixed input. So what you are doing two ways: setting the initial pressure at a fixed value, or you can setting the flow rate to fixed value. That means when we are calculating, I have to fix either the pressure or the rate, flow rate. So most of the above decisions to be made are neither obvious nor necessary straightforward. So that means when we are trying to do some deconvolution analysis, we should, if there is no some copybook write up or maybe the information which are available and you use specifically that or follow that guideline and you will go for a specific deconvolution. That is not there. Some practical points and guidelines could be used towards defining the workflow for pressure rate and pressure deconvolution implementation. So what there is no specific guideline, but what there are some guidelines, you could follow that, but depending on your situation, you need to decide which test I should go for deconvolution or which part, because we will discuss now the taking different type of, let's say, synthetic information. Okay, so that formulation we have seen earlier, this is actually a convolution integral actually. That integral, so once you do a D part, that will give you some input. So this implies that the kernel function GT, okay, here remains the same and thus its parameters as thickness of formation, permeability, porosity, CN. So these are what we consider this parameter remain constant. That we have to make linear. Then actually we get the response function right, and which then it will be proper to utilize this deconvolution for estimating the specific parameter of a reservoir. So that means what you see, there are possible instances where the linearity of the convolution integral could be violated. So if I just go back, you see the data. That means we are considering this parameter will be linear. Okay, that means these parameters will be linear, means depending on the variation, we should make it linearized. These parameters when we are performing the deconvolution. Okay, but you see so many, as we have a lot of idea why the problems may occur. I'll just read out the points so that it will be easy to understand what are the different instances of the which could violate or linearization or inconsistency of your data. Okay, so during cleanup sequence, what is the cleanup? When a well is started to produce, we try to change the bin size so that flow rate should change, and whatever the problems around the wellbore or maybe some maybe damage to the wellbore, that should be cleaned out. Okay, so that is called cleanup. So where the skin factor caused by mud filtrate invasion and completion fluid decrease as the formation of flask by the production rate. That means we are changing the bin size to change the production rate to less production, then gradually more production. So that's why your whatever the damage done to the mud filtrate or maybe the completion fluid, that may be cleaned up. Over long periods of production, the wellbore skin factor may change due to calcium carbonate. That means what? Let's say we are testing one initial build-up. After a long time, we are going to perform another build-up, and we are taking for both the build-up for our deconvolution. But that is not possible, because what in between time of production, you may have some skin develop. Okay, so that may give you the possible difference in the deconvolution of the first build-up and the second build-up. So that means with time, we should be careful enough to take care which should be an optimum or which voltage should be taken care for our deconvolution. So workover stimulation, you know, workover is a job which we do, or stimulation is the activation or maybe increasing the wellbore surrounding damage for our flow. Operations over time may change the effective thickness of flowing interval and a formation of damaged skin. So these are some of the activity we do in the to enhance our production, okay, for individual well, and that can change your wellbore surroundings. So once you do that job, so that means initially if you perform certain sort of build up and then you follow or you do certain work of a job or done the stimulation, then again you are doing a build up. If you are taking two data together, that will give you different result. So that we will see. Okay. Volvo storage coefficient for a drawdown and build up test may not be set for the deconvolution period, but because what two cases are different. Why? Because when we are removing crude oil or maybe any sort of fluid from the wellbore, the effect in the pressure and when it is basically we are closing it, the two things are different. Okay, so that's why when we could not take both the data for getting the deconvolution. The fluid compressibility and viscosity may change due to its pressure dependence, such as gas condensation. So that cannot be, sometimes that will vary taste after taste. That is also one which could give us the inconsistent data to perform our deconvolution. Change in the kernel function parameters due to formation compaction. Okay. So whenever we are generally it's very less, but sometimes it may happen because you see if loose formations are there when we are cleaning the or maybe we are reducing the pressure of the fluid inside your pores, that may sometimes it may collapse or it may compact. Okay, so that can change your actual your response function due to the change in your parameters value. In the presence of multi-phase flow in the vicinity of the wellbore due to gas evolution as the flowing wellbore pressure goes below the bubble point pressure. So as we see, whenever we are trying to see the pressure changes right from the wellbore to the, or you can see infinite radius to an wellbore. So pressure is gradually decreasing towards the wellbore. So maybe near the wellbore area, if the pressure is below the bubble point pressure, so gas will evolve, and then that can change your scenario near the wellbore. Okay, so that is how you may not get the linearity right from your wellbore to the air from wellbore. So moving fluid bank or aquifer water flux in the reservoir during the deconvolution period. So now whatever you see, whenever a aquifer fluid is including into your reservoir, the behavior, that is the compressibility parameters of your crude oil or gas or maybe the aquifer water may not be safe. So that's why that can change your that can disturb your linearity functions. Okay, so it would be very optimistic to assume that the superposition principle holds in earnest for the entire duration of given pressure transient test, particularly for very specific information of your wellbore. Okay, so that is the production test, long production, very long production test. That is how we are trying to eradicate certain inconsistency and try to get the data. Okay, so that is one part which is very advantageous. So if our deconvolution parameter for different tests are lines are really matching, that means we have really linearized. So while pressure rate deconvolution equals a complete production rate history, only a subset of the pressure data can be used to obtain a deconvolution response corresponding to the entire duration of the test. So this is the advantage. You know, when we are doing so many consecutive tests, sometimes we may have different tests, and that time you may have a skin. But after sometimes your skin has been removed, so that time the test may be, the third buildup may be very good. So we'll see today with some of our synthetic example how depending on your variation in your response or depending on your time of test, you will get the different response functions. Okay. So what might be less straightforward to identify is how, for instance, a single buildup can bear information about the entire flow sequence that would allow for a determination of a deconvoluted response for a time interval potentially much longer than this buildup. Okay. So this is less straightforward. So that means we are getting, because we are putting a logarithmic scale. So that's why small time now can be extended to a long period. So this is what we are trying to. So now I'll just discuss two synthetic example here. You see here the dotted line is giving you the rate and the solid line is giving you the pressure response. Okay. So this is first drawdown, then we have the second drawdown, and then we have a build up. So you can see from the rate value, so initially up to T1, it's a different rate, then we follow a different rate up to T2 time, and then we are following a build up. So it is very much clear that the build up response in the figure is strongly affected by the final rate. Okay. Because your initial rate was, this rate was very high. So that's why build up. Okay. So, but also affected to some extent by the early build up rate. So the deconvoluted, if I just go and see the deconvoluted response, you see all the here, the build up, the deconvolved, and the model. Here all the lines are there. Okay. So if you see here the first one, Then here both the values, the triangle and the cylinder, both are following very nicely. Okay, and we have got a straight line slope. Okay, straight line domain. So you see second build up. This is the first build up. Okay, and this is what the model, the solid line. Here the solid line. Okay. So figure present superposition of all the, because what is there? You see here we are putting the derivatives, pressure derivative with respect to time. How? Because we are getting the rate pressure. Okay, rate pressure with respect to rate. We are trying to get pressure and we are doing a derivative of that. So as the deconvolved response is presented at logarithmic scale, even significant gaps in terms of available response. So let's say you are missing certain response, you are getting certain response noisy. So you can eradicate the noise and try to get a single response or maybe a response which may give you a better information. Okay. So significant gap in terms of available response in linear terms becomes small at such a scale. So when you are changing it to logarithmic scale, that time simple gap in your linear time interval maybe not basically giving you much information. It's not so important here. Most of the response interval can be defined based on the pressure response from a single build-up, and in the short interval where information is missing, the smoothness, consistent imposed terms in the curvature actually changing right from different part. Okay, so this is what, so the smooth and interpretable response to obtain is obtained faithful to show nature of the diffusive event, because diffusive event is very small and we are trying to get the response maybe from individual. So what is there when we are doing any build up or any drawdown, actually we are, or maybe the consistent pressure flow rate. So all we could take care, if we function, all the functions we linearize it, then we could get certain information. Okay. Now the deconvolution process makes it possible to use only a few selected consistent data subset to obtain a deconvolved response. Okay, so this is most important part. So you can see, even if you have noisy data, we could erase the data. We should not consider the data for our deconvolution. This could be the case of a single build-up as shown above, or of only a selection of several high-quality build-up, or the last drawdown sequence followed by an ensuing build-up. Okay. So thus, while an entire test is unlikely to exhibit a consistent response following the convolution integral, using only part of the pressure data satisfying this condition makes deconvolution an attractive technique. So this is what the advantages means. What if you perform a repeated test, okay, which I'll see, we'll see it in the next synthetic analysis. So while this property, obtaining reservoir information for the entire duration of the test, makes deconvolution a practical tool for interpretation, it should not be inferred that by extension of this property, a good deconvolved response could always be obtained from an extremely short buildup. So this is what the problem is. So if you just do a short interval test, that cannot give you, or that cannot be giving you the entire duration of the test, or maybe right from your wellbore to an extended directions. Okay, so this is what the problems are. So you may have to get the reasonable response so that you could extend it, or you can extrapolate the information for your better, or maybe extrapolate the information for understanding beyond the test time also. Okay, so the information content and quality of the data are still critical to make the deconvolution workable and provide representative results. So what that means, this is beyond the time of test. We could go for it if our data is accurate and if we really do good convolution. Okay, so now here, okay, so the same thing here. In the provided example, significant constant. So you can see all the three data is matching. Applied to obtain good results such as imposing both flow rates and initial pressure as forcing an extremely high quality match. That means in this specific case, what the last build up, even if you go for the build up only, deconvolved as well as the model your deconvolved data, all are matching. So we have a very quality data and all could be used for getting our response and the reservoir characterization. So but the next synthetic diagram, if I show you, that is slightly different. So for decision selecting which flow period to consider for the deconvolution process from available pressure data is a critical first step in ensuring that representative deconvolution results are obtained. So that means being a practicing professionals or maybe practicing engineer, when we are trying to do our analysis, we should be very cautious about selecting certain information or data which should give us the most result, most best result. Okay, we'll see in the next uh, discussion. This is another synthetic example which will give you much better information on how specific subset will change their information in terms of extrapolated information. So here you can see we have a three build-up. In order to assess the data, we have three build-up. Okay, and we have, this is actually the your, you can see that this is the flow rate and this is your pressure response solid line. Okay, so this is actually clean up. Then second, this is flow after flow test. That means we are using multi-beam to understand the flow pattern. Then the last build up for an extended time. Okay, so what multiple drawdowns with three build up period for a fully penetrated vertical well. So this is actually synthetic example how we could use different information to understand our deconvolution and the reservoir parameter. So what the provided information, thickness is 100 feet, reservoir parameter 30, porosity is 0.20 mu. So this has been linearized parameter. Okay, so that means it will be consistent throughout the reservoir. That we have taken care. The reservoir model assumes having a two parallel no flow fault at 300 feet and 1200 feet. We'll see that away from the well. Okay, so this sometimes what we really need to see certain conventional technique also to match our deconvolved data. So it should be stated that only the closest boundary, closest boundary 300 feet can be identified from the individual build-up test. So that means as our time of the build-up is not much time, so that's why the closest boundary, which is 300 feet away from the well, may be understood. Okay, the test consists of the three main periods. What I told, the initial short flow period. So this is a short flow period. Okay, then what we follow a clean up. Assume a clean up when we just change the beam size. Okay, clean up. Okay, then we another your multi flow rate. Okay, so flow after flow rate. Initially, you see here your pressure is not reached up to that, so that beam size is slightly higher. Here it is a zero. So initially some build up, but we could not consider build up because we should not stabilize it. Okay, so then we use different beam size to flow after flow test. Then again we go for a extended period of a build up time. So this is the final build up, which is extended period, but in these two cases it is not. Okay, so this is the part. Now what you see, the reservoir model consider here assumes skin factor of 115 during the first drawdown. Okay, so now what, when we are this drawdown, the skin factor is 50. Then what happened? Gradually decreasing to 0 for the last two build up. Why? Because this is a cleanup activity we are doing. Once we do the cleanup activity, the skin becomes 0. Okay, so that means when we are now using this build up 2 and 3, maybe build up 1 deconvolve or this short build up may not help us to understand the real picture of the deviate. We will discuss that. Okay, so in the model, a Volvo storage coefficient of this per psi is used for both drawdown and build up test. Surface certain is assumed except for the last. So what is happening? So you see the procedures are different. In these two cases, we close superficially, but in the third case, it is basically downhole setting. Okay, downhole setting is used of this build per psi. So Volvo storage coefficient, random noise are added in both drawdowns, okay, and build up. So we are putting some noises. So then what, the contaminated pressure and flow rate are called measured pressure and flow rate as if they were measured. Okay, so this is what our two parameters, this is recorded and this is the measured in the synthetic data, and what is the sequence of test. Now what we do, you see here, it's a very clear to you. Hopefully, if you remember our initial part of the pressure part, so you could understand this is the Volvo storage effect. Okay, so in this example, the linearity of the convolution operations equation is deliberately violated. That means we have inconsistent data. Why inconsistent data? You can understand build up 1 and build up 2. You have 2, the effects are there, because what we have discussed, initially the available storage as well as skin was there, but after that maybe during the third build up, we may not have the available storage effect as well as the skin. So as stated above, for the first two build up tests, it is assumed the surface certain is used, while for the last one, downhole certain is used, downhole certain. So you can understand this is the effect of the available storage. So as we have performed the surface certain, so that's why you have the two effect, which is available storage effect as well as with skin. Okay, but in the third case we perform the downhole setting. That's why you see there is devolved avenue available storage effect. Only maybe some effect of skin we may get because our skin will be there. Okay, so furthermore, it is assumed that the filtrate and completion fluid invasion created a significant skin factor in the two cases. That's why you see we have discussed earlier, depending on the up and down part, rather than the zero skin is giving us the skin factor. This is more skin, this is less skin. Okay, so you can see this is the first build up and this is the second build up. In the second build up, as we perform our clean up test, so you can see the skin has reduced significantly in the second build up. Whereas third build up, skin is there but not in that much. Okay, for the first drawdown, which gradually decreased during the production period. Okay, so that is how, that means when we are performing, we should be very careful how we will try to linearize the parameters. Okay, the same thing you see, this is the deconvolved. Okay, so one is only we are considering build of 3, deconvolved and the true. Okay, 3 parameters are there. So what, this is a complete deconvolved right from the 0.001 times, so this is a log scale. Okay, so due to the change in the skin and the available storage of the model among the 3 build-up periods, only the last build-up will be deconvolved initially. So we are initially testing with the third deconvolved pressure. Okay, the solid line. This dotted line is true, and this is your build-up 3 only, the dot part. So you see it's very much matched with, okay, with your model and the build-up 3, but whereas the true part is not matching. Okay, so very good match is obtained for the pressure history where the flow rates are essentially left unaltered by the deconvolution process. The deconvolved pressure, derived pressures are matched very well with the derivative of mu3, but does not match the derivative of the true model, because true model may be slightly different. Okay, so that is the part which we have to. Okay, in fact, the deconvolved derivative only maintain the trend of the build-up 3 derivative until the end of build-up 3 and then goes up slightly. Okay, so you can see here. So this is actually your deconvolved part, slightly goes up, whereas it is followed up to this part. Okay, so this is our deconvolved. That means we could extrapolate it also after that information. Okay, so now same thing here. So both du3 and deconvolved derivatives show here exhibit signature of a single no-flow fault. So once you got single no-flow fault, means we could understand where the second infinitely acting flow result is apparently due to the half infinite system. Okay, so that means you can here you see it's a continuous. So that build up may not reaching the second part. That's why you see this is pseudo steady part. It is going up with maybe slope. Okay, but here it is not there. That means the time we perform, that is not giving us the second fault, which is far away from your, and you could not reach that. Okay, so the semi-log slope derivative towards the end of the BU3 becomes almost twice the first infinite acting period. So this is the infinite acting period. Okay, that is going, but it is then without any other data, one may conclude from both BU3 and deconvolved derivatives that we have an infinite reservoir with a single no flow fault. Okay, so here from this term you are not getting the second part. Okay, so these two build-up derivatives and the deconvolved derivatives for which only the last build-up data are used without added constant. Okay, so this is what from the derivative and of the true derivative. These are distorted signature due to superposition effect, but not the true reservoir behavior. Okay, so that what is happening in that. Now, if once we add the second part, so now, so okay, the behavior discussed in the above paragraph, whereby the deconvolved derivative only extend the conventional derivative in the artifact of the curvature consistent use for this deconvolution where limited data are used. Okay, so you see this is your B3, but you are going up to a certain, so you could extend certain time, but you cannot get the actual data response which is true here. Okay, so that means it is giving you certain extend extrapolated information but not up to the specific time period which we wanted to get. Okay. So now you see the second build-up will be include. So in this case, we have the two build-up. So the true and build-up derivatives and the deconvolved derivative for which the last two build-up data are used without added constant. So once we take, you see this is the now dotted line is deconvolved. Here the deconvolved. Okay, this is the solid line is true and this is the only BU3. When we are adding, because it is not consistent data, we have discussed earlier. Okay, so lead to instabilities in the derivative response because the linearity of the convolution in Figare was violated by change in the available storage in the model response these two periods. So we have discussed earlier because in the second build-up we have some effect of available storage effect that is now actually distorting your derivative at the end. So it appears to you. So in the when we are going for this show, so the deconvolved derivative obtained by using both B23 and B2, BU2 and BU3 pressure data exhibit an oscillatory behavior at the late time. Okay, even creating a slight distortion of the first infinite acting region. You can see here the first infinite acting domain also is creating certain disturbance. It is not matching exactly. So that means selection of your data, test of data is very important for proper analysis of your system. Okay, so this is what we are discussing here. By if you use the subset of data for getting our deconvolved pressure analysis. Okay, so here the deconvolved derivative is greatly improved by using the part of this. Okay, so this is true deconvolution. Okay, so although it is still slightly different from the true model. So now what is there? You see part of the last flow period along with the last build-up. So this this dotted deconvolution, what we have considered last production little bit. Okay, so that means the first one is only build-up 3. The second graph we have discussed, which is giving a late time problematic due to the available storage of the build-up 2. But here what we are considering? We are considering which are only the last flow period and the build-up data. Okay, so that too we are considering for this deconvolution. So you see it's with the matching with the very much with the true. Okay. In this case, the deconvolution process requires assigning different error bound to drawdown and build up pressure data because each data set has considerably different noise characteristics and level. So what we discussed earlier, when you just I'll go back for the initial graph. Okay, so that will give you, so you can understand here. So this flow period we consider in this case third. So initial part we are considering only the third build up part. The second case we are considering only the second build up along with the third build up. And in this third case, we are considering this part. So from this flow as well as this flow, it's a long time. So that may give us certain real informations with slight deviation from the actual. Okay, so this is what is there. You can see. Okay, so each data set. So you can see here. So that means this 3 graph I put together. Okay, so one you see only the last build-up we are considering the subset of last build-up we are considering here. Here we are considering the build-up 2 and build-up 3 data for our deconvolution, and the last one we consider the last flow period and the third build-up. Okay, so it is important to determine what subset of data among production and build-up period should be used for deconvolution. This is very important for us to discuss or to understand which subset of data is really giving me a good match of my actual predicted system. Okay, so although it is assumed that flow rates are known exactly without measurement noise, in the 3 deconvolution case, deconvolution of the single build-up period without using constants could be still uncertain and thus fail if the data are inconsistent. Okay, so you could now get the idea how we deconvolve our test and particularly the flow rate data for getting our information right for the system. Okay, so combining the consistent part of drawdown data with a build-up period can considerably improve deconvolution results. So in the last case, you can see this is actually the true. This is the third build-up, and once we add some time of the production period, this is more or less matching. So that means each and every part will give you a disturbed situation if our data subset is not proper. Okay. So in reality, it will be difficult to define consistent and inconsistent parts. So that is how real understanding is very important when we are really moving for getting our analysis done. Okay. So that is what we discussed in our this class. So that means what Deconvolution is nothing but an mathematical operations by using which we try to get the information where we linearize our parameters. This is a parameter to get the reservoir understanding right from the wheelboard to the from the wheelboard. Okay, so this is what our discussion. On this